Okay, so this is trigonometry. This is the first section that we're going to go over. There's a lot of terminology in this first section, and it's just easier if I just pulled up these notes and we go through it together, and I'm going to insert some other problems in there and go through other questions. So first of all, what is trigonometry? Trigonometry deals with triangles and angles and the relationship between the sides. So here, a trigonometric function. So you deal with functions before, like f of x equals some equation, x squared plus 2x plus 1. And if you wanted to plug in a value in there, you would plug in a value like f of 1. You plug in 1 wherever you saw an x. So this is just a function, just like what I had said. So trigonometric functions, we can also call them circular functions, and we'll look at that trigonometry as it relates to circles. So these are functions of angles. They are used to relate the angles of a triangle to the lengths of the sides of the triangle. And they are important in modeling periodic phenomena and among other applications. So you'll see that later on in this course, when we're looking at our trigonometric functions, sine and cosine, especially, those are related to like the tide, how the tide comes in and the tide goes out. And how when we can use that function to relate when it's going to go in or out, high tide, low tide, etc. Okay, so let's begin with just defining a few things in here and vocabulary, like I said. So looking at this, we say that a ray, and you can see this ray in here. All this is a portion of the line that starts at this point V and that extends out indefinitely in one direction. So the starting point of V of the ray is called our vertex. Okay, so if we take this ray here and we put two of them together, one starting at, or both of them starting at this vertex, then they form an angle. So one ray of an angle is called the initial side. And the other side of the angle is called the terminal side. Okay, so we're starting here. This is our vertex. We have this initial side that's on the bottom, and normally we'll put it horizontally like that, and we'll put it on the Cartesian plane, the x and the y axis, actually on the x-axis, positive direction, but it can be other places. But normally this point here is the initial side, and then if we take this and we swipe it up, then we get to the terminal side. Just gonna pause for a second. Okay, so this is better so that you can see my hand. So we have this ray, it's in the horizontal position, starting at the origin. And this is what we're normally going to do. And then we're going to take it, we're going to swipe it either counterclockwise or clockwise. And after some angle, we're going to stop, and this is going to be called that terminal side. The angle, a lot of times we use Greek letters like beta, alpha, or sometimes we also use capital letters to denote that. So here's a case, that first example, that one in green that I was showing you with my initial side. Notice that this is going counterclockwise. So when we go counterclockwise, the angle is always positive. Notice this second angle. So our initial side is here. But this time when we rotated it clockwise. And so when we go clockwise, the angle is considered to be negative. So here is an example where we are starting at the initial side. We are going and rotating counterclockwise. So it's going to be a positive angle. But notice that in here, we've hit our initial side and we pass it and we get to this terminal side. So this was counterclockwise and it's a positive angle. So there's an infinite number of ways that we could get to this terminal side here. We could have just gone up this little piece, that angle, or we could rotate it a full revolution and get back there. Or we could even do another revolution or an infinite number of revolutions to get back to this terminal side. And so that's going to be helpful for us later on, where we can take the smaller angle if we are given a bigger angle and deal with it. So as I mentioned, it's quite often that we use Greek letters to denote angles. So there's a couple of Greek letters down here and their names if you don't know them. This first one is called alpha. The second one is called beta. And this third one is gamma, I believe. Could be wrong on that one. Usually we use theta. So an angle theta right here is said to be in standard position. If this vertex is starting at the origin, like we had talked about before, we have this rectangular coordinate system, and the initial side coincides with this positive x-axis. So here in this first example in this box, notice that we're rotating again in the counterclockwise direction. And so again, our angle we would say is positive. Where this second example, again, we're on our initial side, it's in standard position because it's on that positive x-axis, but now we're going clockwise. And so to get our terminal side, the angle went clockwise, so our angle then is considered to be negative. But again, there's multiple ways that we can get from that initial side and standard position to that terminal side. I could have, in the second example, instead of going this direction theta, I could have started on the initial side, went counterclockwise, and I could have came and stopped at this terminal side. And so this positive angle would give me the same terminal side as that negative angle. And I would probably, maybe I would name this something different. So when an angle is in standard position, the terminal side will either fall in a quadrant. So recall when you have your X and your Y axis, we had 4 different quadrants. This one in the upper right corner, that one is quadrant 1. And we use the Roman numerals to denote those numbers, the quadrants. And then we go again in the counterclockwise to put this. So this one in the upper left-hand side, this is our second quadrant. The one down here on our lower left-hand side is the third quadrant. And the one down on the lower right-hand side is our fourth quadrant. So when it's in standard position, that terminal side, it's either going to land in one of those quadrants, 1, 2, 3, or 4. And in that case, we'll say that theta lies in a quadrant. So a lot of times we'll say, okay, like I said before, we can do different angles, but we could say this angle ends in quadrant 2. And that's going to be helpful because in that quadrant, we know if our x value or y value is positive and negative, and we're going to use that a lot later on in the course. So knowing which quadrant where terminal side angle is landing in, but it might not land in one of those quadrants. Instead, we might fall on the y-axis, or we might even fall on the x-axis. So if that's a case where our terminal side falls on either the x or the y-axis, we say that these are quadral and I can't say it now, quadrantal angles. Quadrantal. Okay. Let me pull up an example, and let's do a couple of examples relating to what we had just talked about. So let's say, actually before we do that, let's go a little bit more into some more terminology. One more thing I wanted to talk about. So let me pull this up. Okay, so far when we've been doing mathematics, we usually use angles, we'll use degrees. Later on, we're going to look at things as being radians and changing things as radians. So it says thus far in our mathematical career, you've probably measured angles in degrees. 360 degrees represents one complete revolution. That's one blank. I didn't understand what they wanted there around a circle. So this means that 1 degree is equivalent to 1 over 360 of a complete revolution. So let's just, again, so we start on our positive x-axis on our initial side, and we do 1 revolution. That's 360 degrees. So if we break that down into 360 parts, that means 1 part is going to be 1 degree. So that's equivalent to 1 over 360th of a complete revolution. So if we're looking at 60 degrees, so that would be 60 over 360, or 1/6 of a complete revolution. So if we go 60 degrees, another 60 degrees, another 60 degrees, there's 60 degrees within that 360. It's one way to think of it. So if we're looking at it and we go up from our x-axis to our y-axis, positive, so counterclockwise, that's in here, we know that that is going to give us a right angle. And so this is 90 over 360, which if we reduce this down, and a lot of times in this class we're going to have fractions, we're going to want to reduce our fractions. So this reduces down to 1/4 of a revolution, and counterclockwise direction, like we said. So if I went clockwise, that would actually be 270 degrees. Anyways, so going counterclockwise, 90 degrees or 1/4 of the way of 360, this is going to be 90 degrees. So starting at our x-axis, if we go counterclockwise to make a straight angle with that terminal side, this is 180 degrees. and this is a half of a revolution counterclockwise. It's 180 degrees, which I just said. Okay, so it's important to be able to draw our angles. We're going to be doing that over and over again for a lot of this course. And so again, a lot of the times we're going to take it and we're going to start on the XY axis. And we're going to have our initial side on the positive x-axis. So we want to look at the following, and we want to identify which quadrant it is in and draw our angle. So 135 degrees. So if I go counterclockwise, because it's positive, I know that when I hit the y-axis, that is 90 degrees. So I know if I take away 90 from 135, I have 45 more degrees to go. So that would fall about right here. So this is 135. And this falls in quadrant 2. And so mathematically, I can write this with this kind of, looks like a rounded capital E. That means contained in. So theta is contained in our quadrant. So I'm just going to put capital Q for quadrant 2. So example B says, let's look at this angle and let's draw negative 120 degrees. Remember, negative angle means we're going to go clockwise. And so starting here at the origin, taking our initial side in standard position, we're going to go negative 120 degrees. So going clockwise, I know that I have to, once I get to the negative y-axis piece, that's negative 90 degrees. So I need to add another negative 30 degrees. So I'd say that theta here, this theta, this is contained in quadrant 3. So let's look at these 2 examples, and let's identify at least 2 more ways, 2 more angles that would get us to this terminal side. So if you're watching this video, then just pause it and think about it and come up with 2 different degrees that would get us to 135 degrees from this first example, and 2 degrees angles that would get us to negative 120 degrees. How about have one of them be positive angle and one of them be a negative angle that gets us to the 135 and negative 120. So now that you've had a chance to think about it, let's talk about 2 choices, but there's an infinite number of ways that we could get to those terminal sides, both positive and negative. So let's look at the following. So again, that first one was 135 originally, which got us here. So one way that we could get back to this terminal side is do a full revolution from this 135 degrees. So another 360 degrees from this point. So if we do that, so making a full revolution plus that 135 degrees. So that's 135 degrees plus 360 degrees, which is going to give us 495 degrees. So that's an example, one example, but we could do 2 full revolutions from that terminal side, and that would give us another positive angle and another angle that would get us to that terminal side. So negative angle. So if we think about this with a negative angle. So again, starting at our standard position, going in the negative direction, we'll write in here that we know is negative 180 degrees. In here, it's kind of helpful to determine where this terminal side and the angle between that terminal side and the x-axis is. And we'll use that later on too in the course. Well, if this was 135 degrees originally, to add up to 180 degrees, which gives us that straight line, 135 take away from 180, that's 45 degrees. So knowing this right here, that this is 45 degrees, I know my negative 180, again, we're going clockwise, plus that negative 45, that's going to give me negative 225 degrees. So one answer was the 495, and we just came up with negative 225 degrees is another angle that would give us the same terminal side. So same sort of idea. Looking at this negative 120 degrees, it's really important to be able to figure out what is that small angle that is with our terminal side and that forms with the positive or the negative x-axis. So in this case, because it's in the third quadrant, this little angle in here, it's helpful to know what that is. So if that's negative 120 and halfway is 180 degrees, I know that in here, this little piece is 60 degrees. And so if I go negative 120 plus a negative 60, because they were going in the clockwise direction, that's going to give us back, sorry, that's not what I wanted to say. That's 60 degrees there. So one way we can get that, another negative, is again to do a full revolution here. If we go clockwise, and so we have negative 120 plus a negative 360, because that's another complete revolution. So negative 120 minus 360. So adding two negatives, you add them together and it's negative. So this gives us negative 480 degrees. So knowing again that this piece in here is 60 degrees, that would form up with the negative x-axis. We could go in the counterclockwise direction. So starting at our standard position, initial side, this right here is positive 180 plus the 60 degrees that we formed from this negative x-axis in the terminal side. So 180 plus 60. That gives us 240 degrees. Okay, so there are some examples you should be able to look at and draw angles given. You should be able to tell which quadrant it falls in, or if it doesn't fall in a quadrant, that which quadrantal angle it is. Is it on the x-axis or the y-axis, positive or negative? You should be able to come up with other angles that would give us the same terminal side. Okay, so there's different ways that we can denote these angles. Right now, we've just been doing degrees, but we can take degrees and we can rewrite them as degrees, minutes, and seconds. This, I believe, is used in navigation. They use this degree, minutes, and seconds. So let me just kind of read through this, and then we'll talk about it, and we'll do some examples where we convert decimal degrees into degrees, minutes, and seconds, and angles that are in degrees, minutes, and seconds, and going back to decimal degrees. So you should be able to convert back and forth. Okay, so degrees, minutes, and seconds. So when measuring angles in degrees, fractions of degrees are often represented in minutes and seconds. So note that the words minute and seconds used in this context have no immediate connection to how the words are used as amounts of time. So when we think of minutes and seconds, we're thinking about time, but don't think about that here. So degrees, minutes, and seconds are used for things like latitude and longitude on topographic maps. And so it's important to know how to convert from degrees, minutes, and seconds to decimal form and the reverse. So that's why we're learning this. So we talked about if you were looking at a full circle, so starting at our initial side and rotating in a full circle, that was 360 degrees. Each degree is split up into 60 parts. Each part is called minutes. So 1 minute is denoted by this one with a kind of like a prime here or a dash up here as an exponent. So this 1 minute is denoted by that number, and it's 1/60 of a degree. So 60 minutes is equal to 1 degree. 60 minutes is equal to 1 degree. And 1 second is denoted by this 1. Instead of 1 prime here, we're going to have 2 of them. So it kind of looks like 2 dash marks in the exponent. So this is 1/60 of a minute. So 60 seconds is equal to 1 minute. So here we're going to be converting back and forth. And so this is, think about something like we're going from miles per hour. And instead of miles per hour, we want to know how many feet we're going per second. And so in order to convert from that, we're multiplying by these fancy ones, like I like to call them, in order for our units to cancel out. So let's say that we want to, let's look at an example here before we jump into this minutes and seconds and converting back and forth between that and the degree decimal. So let's say that we are going 60 miles per hour. So 60 miles over 1 hour. Why am I doing that? 1 hour. So 60 miles per hour. And we want to convert this to, let's say, feet per second. Okay, so let's first deal with the miles. We need to figure out how many feet there are in 1 mile. So how many feet are in 1 mile? So we have 5,280 feet is equal to 1 mile. So I want the miles to cancel out. So I know that I want the mile in the denominator. So if I multiply or divide both sides of this by 1 mile, that is going to give me 1 is equal to 5,280 feet all over 1 mile. Okay, so that's going to get my feet. Now I need to convert my hours to seconds. So I need to figure out how many seconds in an hour. So 1 hour is equal to, well, I know that it's equal to 60 minutes, and I know that there's 60 seconds in a minute. So that's going to be 60 times 60, or 6 times 6 is 36, and then we have 2 zeros. So 3,600 seconds. So I want my hours to cancel out in this denominator over here. And so I can multiply this so that I have hours I want in my numerator so that it can cancel with the hours in the denominator here. So if I divided both sides of this by 1 hour, I get my fancy 1. So 1 hour and 3,600 seconds. And so now we can start simplifying. So notice that I have miles. Those units cancel, hours cancel. And so we're left with feet and we're left with seconds. So we're going to have feet per second. So let's reduce this down. I noticed that I'm dividing by hundreds. Like here is a 0 here, so I can cancel one of my zeros in the denominator. Or I'm dividing those right there by 10 on each. So cancel. I noticed that 6 goes into 36 6 times. And let's see, does 6 go into 528 evenly? It does 88 times. And so we have 88 feet per second. So if you were going to travel 60 miles per hour, that's the equivalent to 88 feet per second. And so that kind of conversion, and we'll need to be able to do that in some of these word problems that we're going to get into later on, and converting these units to get them to what we want them to be is helpful. It's also helpful when we're looking at these degree, minutes, seconds, and we want to convert it to decimal degrees or decimal degrees to degrees, minutes, seconds. And so we're going to use this fact here that we have, that 1 minute is equal to 1 over 60 degrees, or 60 minutes is 1 degree. This 1 second is equal to 1 over 60 minutes. But sometimes we want to convert that second just to degrees. So to do that, 1 second, that's the same thing as 1 over 3,600 degrees. So let me make some room on my screen. Okay, so let's look at an example. So in front of us, we want to convert this 45 degrees, 10 minutes, 15 seconds into decimal form. So first, let's ignore the 45 degrees and let's just work with our 10 minutes. So we have this 10 minutes here, and we want to convert this into a degree. And so let's rewrite that fancy one. And so we know that 1 minute, again, was equal to 1/60 degrees. And so we need to divide by a minute. So we can have minutes down here. And so this is like 1 minute in the denominator, all over 1/60 degrees. Well, that's the same thing because we have a, actually, let's write it like this. Let's just write it like this. So we can cancel that 1 minute cancels with this minute up here. And we have 10 times 1/60. So this is giving us 1/6 of a degree. It's going to want us to round, and it's going to want us to put this in decimal, but we want to wait until the very end before we start rounding. So we have this is like 45 degrees plus this 1/6 of a degree plus, now let's take this 15 seconds. And we want to convert that into degrees. Well, we just mentioned that 1/3600 degrees is equal to 1 second. So now our seconds are going to cancel with one another. And we have this 15 all over 3,600. And this is in terms of degrees, but we can simplify because 15 goes into that 3,600 evenly. 240 times. So this is 1/240 degrees. So in order to add those fractions together, we need a common denominator. So getting our common denominator, I notice is 240. So have this, just make some room. Let's just do it over here. We'll come back to this later. So this is 45 degrees plus, so I know 40 times 6 is 240. So this would be 40/240 is the same thing as 1/6 plus 1/240. That's going to give us 40 plus 1, so 41/240. So this is 45 degrees plus 41/240. And it wants us to round that into decimals. So taking 41 divided by 240. This is approximately 45 point. So 41/240. So that's 0.17083 with a bar over it. So going out 4 spots, 1708. 3 with a bar over it, that 3 is going to keep that 8 the same. So this is approximately 45.1708 degrees. Is the same thing as 45 degrees, 10 minutes, and 15 seconds. Let's look at another example. This example, we're looking at 9 degrees, 9 minutes, 9 seconds. And we want to convert this to a decimal degree, and we want to round 2 decimal places. So again, you want to break this down into pieces. So ignoring everything but like the 9 minutes. Let's look at the 9 minutes. And let's convert that into the decimal degree. So again, we know that 1 over 60 degrees divided by 1 minute is 1. And so the minutes cancel, and we get that this is 9 over 60. Well, I know that they both have 3 in common, and so I could break this down as 3 goes into 9 3 times, and 3 goes into 60 20 times. So 9 minutes is equal to 3 over 20. Or 3/20 degrees. So now let's take our 9 seconds and let's convert that over to degrees. And we know that 1 over 3,600 all divided by 1 second. So seconds cancel, and we're left with 9 over 3,600. And this is degrees. 9 goes into 36 evenly, so we can reduce this down to 9 goes into 36 4 times, so 1 over 400, or 1/400 degrees. So we're going to need a common denominator. And I noticed here I have 3 over 20 degrees, and I have 1 over 400 degrees. So I notice my least common denominator is 400. So I'm going to multiply this 3 over 20. 20 times 20 is 400. So this is equal here to 60 over 400 degrees. So 9 degrees, 9 minutes, 9 seconds is equal to 9 degrees plus this 60 over 400 degrees plus this 1 over 400 degrees. So this is going to give us 9 plus 61 over 400 degrees. It wants us to rewrite this in decimal form. So looking at 61 divided by 400. Right now, this would give us 9.1525 degrees. It asks us to round to the second decimal place. So we go out to the third decimal place and see if it's 5 or higher. If so, that would round this up, but it's lower than 5, so it keeps the number the same. So this is equal to 9.15, or approximately 9.15 degrees. So how about you guys try it? So this is part of participation, and I'll have you guys turn this in. So go ahead and convert about 61 degrees, 42 minutes, and 21 seconds into a decimal degree rounded 2 decimal places. So take a moment, pause the video, and do that if you're watching this not live. And if you're watching this live, I'll pause the video and I'll give you a chance to do it, but I'm not going to go over it because I'm going to have you guys turn this in, but I can always answer any questions that you have if you're live. So I'm going to pause the video while you guys work on that. So we're going to look at another example. We're going in the opposite direction. We're going to convert 61.24 degrees into degrees, minutes, and seconds form, and we're going to round to the nearest second. So again, we want to, in this case, have this 0.24 degrees. We're okay with the 61, that whole number, but that part of the degree, 0.24, we want to convert that into minutes and seconds. So let's ignore the 61 for a moment, and now let's just look at that 0.24 degrees. And we want to convert that. Before we do that, let's just remember that 60 minutes was equal to 1 degree. This is the time we're going to want the degrees to cancel. So if I divide both sides by 1 degree, one, and get this fancy one, and I'm going to use as 60 minutes over 1 degree. So looking at 0.24 degrees, multiplying by the fancy one, this 60 minutes over 1 degree. So multiplying 60 times 0.24, we get 14.4. So this is equal to, because degrees cancel, this is equal to 14.4 minutes. The problem is here that we have 0.4 minutes. So we have a part of a minute. And so we want to take that part of a minute and we can want to convert that into seconds. So ignoring this 14 minutes, let's go to the 0.4 minutes, and we want to convert that to seconds. So let's go back and think about our formula. We know that 60 seconds is equal to 1 minute. We're going to want the minutes to cancel so that we have the units of seconds. So if we divide both sides by 1 minute, our fancy one that we're going to use is going to be 60 seconds over 1 minute. So thinking of the minutes as those units are canceling, we have 60 times 0.4, which gives us 24. And now that is into minutes. So our 61.24 degrees, this is equal to the 61 degrees. We're going to use the whole part here, 14 minutes and 24. 0.4 minutes was 24 seconds. Let's pull up and do one more, and then we'll move on to other conversions of degrees. Okay, so now we're going to look at 29.411 degrees, and we want to convert this into degrees, minutes, and seconds, rounding to the nearest second. So we know the whole part of the degrees is 29. Now we want to figure out what the minutes are, and if we have any partial minutes, we're going to convert that partial minute into seconds. And so we're looking at the 0.411 degrees. And we're going to multiply that by 60 seconds over 1 degree. And so multiplying 60 times that, 0.411, we get 24.66 minutes. We want to take our 0.66 minutes and we want to convert that into seconds. So we're going to multiply that by 60 seconds over 1 minute. So 0.66 times 60, this gives us 39.6, and these are seconds. So we're rounding to the nearest second. The 6 is higher than the 5, so that's going to round the next digit up. The 9 rounds up to 10. So this is approximately 40 seconds. So our 29.411 degrees, this is equal to 39 degrees, 66 minutes, and 40 seconds. So actually, we're not done here because we have 66 minutes. And that is actually over a degree, right? We know that 60 minutes is 1 degree. So we need to convert this. 60 minutes equals 1 degree. So think of this as 60 minutes, right? Plus 6 minutes. Well, that's the same thing as 1 degree and 6 minutes. So if we take our 1 degree there and we add it to our 39 degrees, this is going to give us 40 degrees. 6 minutes and 40 seconds. And I guess I'm not awake right now, but this 29 degrees part, I don't know why I wrote it as 39, but that should be a 2. That should be 29 degrees, 66 minutes and 40 seconds. So rounding up 1 degree from 29, that should be 30 degrees. 6 minutes and 40 seconds. So I'm going to stop this recording and I'm going to start a new recording so that this new piece, if you knew all of this stuff here and you wanted to just jump to the next video, you could. So let me stop this video and I'm going to restart a new video so these videos aren't as long.